Hey everyone. Today in this tutorial I'm going to be going over how to model SMA connectors, or in general some sort of coaxial connector, as an input to your HFSS design. So we'll start by opening up HFSS and we'll create some new project. And let's go ahead and insert a HFSS design. Just click on this guy here. Okay. And we'll save this. Save it as something. Let's go to HFSS. And then let's call this, we'll design a filter. Design a filter today. So we'll call this a half wave resonator filter. It's just some device that we'll be looking at as an example for this SMA fed network. Okay, so click save. Here we go. And the first thing we're going to do is go ahead and insert the substrate. So draw some box. And when these guys come up, okay. So this will be, we'll put this as W box as the X size, and that'll be maybe 500 mil. Okay. W box for the Y size, and then for the Z, we're going to make it the thickness of the substrate. We'll be using 4003, Rogers 4003 for this example, 32 mil. So we're going to call this H for the height of the substrate, and 32 mil. Okay. Apply. Oops. I need to put it at the right position. So we're going to put it at minus WB over 2, WB over 2, and let's put it at minus H. So the top of it will be at Z equals 0. Apply. Okay. Oh my goodness, where'd it go? What happened? I broke HFSS. Minus. Good, good. Definitely going to keep this in the video. Okay, so now we're going to add in another box. Oh, we'll call this, we'll name this. This is the substrate. Okay. And then we'll copy it, and we're going to make the ground plane. So substrate 1, this we're going to call it G and D. The ground plane is going to be of thickness T, and the just a typical value here for half ounce copper is 17.5 microns. Okay, and its location will be at minus H minus T. Okay, awesome. And I like to color the ground sort of an orangey copper color, if that's copper, and then make the substrate transparent. Okay, so here's what we've got so far. This filter that we're designing, we're going to actually be feeding from the bottom. So eventually we're going to make cuts out of our ground plane in order to feed it with these SMA connectors from the bottom. But the next thing we're going to do is add in the transmission lines. So let's go ahead and assign these materials. This material, I'm going to edit, and I'm just going to look for it. It's copper. There it is. Okay, that's copper. And then the substrate, edit, we're going to add Rogers 4003. Okay, there we are. So this is our substrate, this is our ground. Let's go ahead and now add in our actual filter device. So half-wave resonator filter is a relatively straightforward device. Basically, you have a transmission line that's a half wave, and you have two output transmission lines that you couple to. So let's sort of copy this ground plane in order to make it. It's going to be that thickness T still, right, which is the thickness of the metal. It's going to be at Z equals 0. And we'll go ahead and center it at the origin. and so we need to define the width of our lines, which I'm going to make 50 mils. So let's define W. That's actually, let's make the Y dimension the transmission line width. So call this W, length, mil, 50, okay. What? I made it small. Oh, right. I actually wanted to make this W. Yeah. And then the length here, the length of our filter is what determines the resonant frequency. So we're going to call it L. And L is a length. And I computed this earlier to be 368 mils to be a half wave at a resonant frequency of 5 gigahertz. So there's L. And let's see. We need to center it there at the origin. So we're going to have it at X equals, let's see, minus W over 2 and Y equals minus L over 2. Okay. So here's our little line. And when this line becomes a half wavelength, it becomes resonant. When it's half wavelength, it's resonant. So you're going to get a maximum of transmission when we reach that half wavelength frequency. Okay, awesome. So we can see that I'm sort of running out of room here for my output lines. So I'll probably go ahead and add in a length for this box. So let's, for the substrate box. So here we go. Let's go into our substrate. And instead of Y being WB, let's make it LB. Call it a length. And we'll make it, let's see, maybe make it 800 mil. Okay, yeah, minus LB over 2. Awesome. And same thing for the ground plane. LB, is that minus LB over 2? Awesome. Okay, so this is our structure thus far. This is our half wave resonator. Sweet. And now we need to add microstrip transmission lines on the top that we're going to couple to. Let's take our half wave resonator, copy it. Let's view this from the top. And we're going to be using a gap between the conductors of 8 mil. So here we're going to take our half wave resonator, shift the position from minus W over 2 to, we're going to add on an additional gap length here. And we also have to add, let's see, would it be W over 2 or W? Let's see. W over 2. Minus W, right? Yeah. So G is going to be length. It's 8 mils. Okay. Yeah, that's exactly what I wanted. Sweet. And this length, we're not going to make any sort of particular thing. We're just going to call it L feed. So length. Let's make it 250 mil. And we want it to go from we want it to start at the origin in terms of its Y coordinate. So it's going to go from 0 to over here. Okay, and this is the feed. This is feed, let's call it feed 2. Because we're going to put port 2 on the right here for just orientation purposes. So copy this guy, and we're going to add another feed, feed 1. Its box is going to be located at, so we're going to add G and add W, and we're going to say that the size is minus LF. Sweet. Okay, so here's our resonant structure thus far. And this is basically going to serve as a filter in the end. We'll see. Okay, so next we're going to need to actually add in the feeding system. So I usually like to round out the ends of my lines. So we're going to add in a circle, centered right here, and it goes out to here. So the center position is going to be, let's just type it in manually, is going to be minus W minus G, right? Yes. And that's for X, I suppose, plus. It's going to be W plus G for X. The Y coordinate is minus LF. The Z coordinate is 0. And the thickness, oh, this isn't a cylinder, this is a circle. Oops. Sorry. Add in a cylinder. My bad. So again, W plus G. The Y coordinate is minus LF. Starts at 0. Radius is W over 2. Height is T. Very good. Okay, sweet. There it is. We're going to copy it. Where's my cylinder? There it is. This is going to be made of copper. Let's make it orange. Copy it. Sweet. And this cylinder is going to be positioned at minus W minus G and at plus LF. Okay, there we have it. So we're going to take feed 1, click on feed 1, and then click on cylinder 1, and click unite. And then we're going to click feed 2, cylinder 2, unite. Okay, there we go. So now we're going to add in, finally, our actual SMA connectors and pins. So the SMA connectors that you'll be using mostly throughout the course are ones that are fed on, are called flange SMA connectors. So they're fed on the surface of the board, and the pin goes through the board. So to model that, we're going to add in a little dielectric puck. So let's view it from the bottom. We're going to add in a dielectric puck. This is going to represent the center conductor here. The exact coordinate is not important because we're just going to type it in. So the position is going to be at, let's see, X is equal to W plus G, Y is equal to minus LF, and Z, let's see, the center pin is going to run from minus H, and then we'll define an additional, let's see, minus T, the length of the ground plane. Then we're going to define an additional input length, LN, and that's going to be the length of our coaxial connector. So LN, here we go, length, let's make it 50 mil. Okay. The radius, standard SMA connectors have 0.9 millimeter diameter, so that's 0.45 millimeter radii. Okay, there it is. So we take a look and we see it's a, did I add a cylinder or a circle? Oh, what was the thickness? Or what was the height? Oops. Let's add. Honestly, I could have just started it at 0 and made this the height. There. Just for simplicity. Less parameters to type in. Okay, so again, just gonna make this like maybe a brass color. A lot of times it's made of brass. So here we go, yellow, sweet. What we'll do is, let's see. I think a simpler way to do this is to go ahead and make the connector on 1, and then we'll just rotate about the z-axis. So the next thing we're going to do is add in our dielectric puck. So let's just copy this cylinder. Oh wait, first of all, this is copper. Or sorry, no, we're going to make it, let's keep it copper. It doesn't really matter. So we're going to say copper, and then we're going to copy this cylinder. And this is going to be the SMA dielectric. And the material of a typical SMA dielectric is Teflon. TEF. There it is. Relative permittivity 2.1. Teflon. Okay. And this cylinder, the radius, the position is going to be the same, but the radius is 1.5 millimeter for the dielectric. And now we need the starting coordinate to be the same as the SMA center pin, but the height is going to be LN. Let's view it from the side, make sure we're good here. Yep. Looks good. And let's change the color. Sort of a gray. And make it sort of transparent. Okay, so we scroll out here. Okay. So there's our dielectric. We also need to add a outer conductor for the SMA connector. So let's see, once more, I'm going to build it out of the SMA dielectric. So let's copy that guy. This is going to be made of copper. We're going to add an additional thickness to the current radius, T. Oh my goodness. What just happened? I didn't put the units, so it's 1.5 millimeters plus T. I didn't like that. Was it like this? Yeah. Okay, my bad. So this is the outer connector, and we're gonna make it a, say an orange color. Actually, let's make it yellow. And then we'll make it not transparent. Let's see, what did I get? There it is. Make it opaque. And we need to subtract the dielectric region from our from that outer conductor. So here's the dielectric. We're going to click on outer connector, then the dielectric, then this is the subtract operation, and we want to clone the tool objects. That way it doesn't delete our SMA dielectric. It just uses it as a subtract component. So now we've got this, basically, if I disable this in the viewport, you can see that basically it's just a little shell, cylindrical shell, which is what we want. Okay, so let's view that again. We also need to, in the SMA dielectric, we actually need to remove the center conductor. So let's see yes. So we're going to select the SMA dielectric, then we're going to select the, I should have named this center pin. Click dielectric, click pin, subtract, clone objects, yes. Okay, there it is. So we've got our cylindrical shell, we've got a dielectric, and we've got our pin going through all the way to the top. But you can see that the ground plane is basically just covering everything. So we actually need to create a new object from this SMA dielectric. which removes that dielectric, that circle from the ground plane. So let's copy this. And I don't actually need the subtract operation for this object. So I have my SMA dielectric, and this I'm going to make it have height ln plus t, and that's sufficient. So you can see now it's poking into the ground plane. So we're going to take the ground plane, then select SMA dielectric 1, and this time let's see, oh wait, before we do the subtract operation, we should clone it so we don't have to do the subtract twice. So right, we're going to select the dielectric, let's name this SMA subtract. Okay, we're going to select the dielectric, the subtract tool, the outer connector, and the center pin. We're going to select all those objects, and we're going to duplicate them around this z-axis. So let's see, I think that's just this guy. And we're going to do 180 degrees. Yep, that looks like it's going to hit right on. And we want to attach them to the original object. That'll just make our lives simpler when we're doing the subtract operation. So click this. Yes, this is all fine. Okay, so now we've got our two connectors on the opposite side of our filter. Okay, so now I'll select the ground plane, and we're going to select the subtract tool, and click subtract. And we don't need to clone the tool objects this time. So there it is. We've got our two connectors. We've got our filter structure on the top, and then the only thing we have left is adding the excitation and the bounding box. Let's go ahead and add the bounding box now. So for simplicity, let's just create it out of the substrate. Now, to truncate the simulation domain and just again sort of make the simulation, just to make the simulation run a bit faster, I'll be using radiation boundary conditions in this simulation. It just sort of allows you to make the domain just a bit smaller compared to potentially using PMLs or using a finite structure like surrounded by free space and then some PML. When you have like microstrip structures like this, which pretty much couple energy from one port to another, this is a pretty good way to model which allows you to reduce your simulation domain. So we're going to call this our airbox. Rogers, make it vacuum. Sweet. And this we're going to put at -h minus t minus ln. So it starts there, and we're just going to make it hb for hbox. It's a length. And we'll make it something like, let's see, you usually want to do at least, I believe the rule of thumb is roughly 5 times the width of the line. But here, let's see, we'll just play it safe, and we'll say 200 mil. So it's well above the structure. Okay. So I think we're ready to go. Go ahead and open up the design here. We're going to add some excitations. So let's check it out from the bottom. Click on excitation, assign. Let's see, I need to select a face first. To go into face select mode, click, hit F on your keyboard. There we go, select this face. Right click excitation, assign, And you've used lump ports before, but now we're going to use what's called a wave port. And wave ports are really cool because they basically allow you to excite a transmission line, or sorry, not a mode of a waveguide mode. So in this case, we have a coaxial line. So wave port will excite that fundamental TEM coaxial waveguide mode. We're going to insert wave port. And we need to define an integration line, which will give us basically our impedance and also like the polarity of of the port. So, what defines plus and minus phase basically. So we'll go from the positive, the center conductor, to the outside. Let's see. If I hit Y, I think, yeah, Y is good because it, there we go. That's what I want. I want to go from the outside of the inner conductor to the inside of the outer conductor. That sounds good. And no need to renormalize. I've designed these SMA connectors to be 50 ohm. These are just standard SMA sizes, but we can check out the port impedance at the end just to be sure. Okay. So that's the first excitation. Now we'll add in a second excitation. Bang. With that, assign wave port, new line. Go from here, center conductor to outer conductor. Next, finish. Okay. We've got our two ports, port 1 and port 2. Basically, you feed this structure from the bottom, and it filters a certain frequency, hopefully 5 gigahertz if I've calculated everything right. So, okay, that's excitations. We need to add in some boundaries here. So this box, press the letter O to go into object selection mode. And we're going to make this box a radiation boundary condition. Right there. Okay, rad 1. Very good. So that basically, if there's any sort of field that's propagating away from the structure, it'll absorb that field and not reflect it back into the computational domain. Sweet. So the next thing we need to do is add in our analysis. So we'll add a solution setup. The primary frequency I'm interested in is 5 gigahertz. These default number of passes is probably fine. I'll increase it to maybe 8 or 9 just to play it safe. Hit OK. And then we'll add a frequency sweep on top of that, going from, say, let's go from 3 to 7 gigahertz. Whoa. And let's do 201 points. Doesn't matter because it's doing an interpolating sweep, so it doesn't actually evaluate all these frequency points. It's just how fine is the discretization on your plot. Okay. I think we are just about ready to go. We've got our box defined. You can sort of check out things here. You've got your radiation boundary condition defined on all the sides. Excitations 1, 2. Yeah, I think we're ready to go. So we'll go ahead and check the design with this button here. Oh, right. So it's a good way to check if you've done something wrong. So you click validate, and it's telling me that the substrate and the center pin intersect. So what we're going to do is we're going to select the substrate here, select the center pin here, and then we're going to subtract and clone the tool objects, and that should have fixed that problem. So now let's validate. Everything checks out. Close and simulate. The next thing you're going to want to do is basically jump through a space-time portal. That way you can fast forward until the simulation is done. So now that your jump through the space-time portal is complete, we're going to go ahead and view the results. So right-click Results, Create Modal Solution Data Report, and the first thing let's check out the port Z0 and see whether or not I got that 50 ohm impedance correct. So new report, And you can see that over the entire range is pretty much 50 ohms. So that's good. Right click. We're also going to check out S11 and S21. So that's how much power is reflected and how much power is transmitted from port 1 to port 2. New report. Oh boy, looks like I either messed up the resonant frequency or something is wrong with the structure, because we're not really coupling any power into the device. Oh my gosh, I think I made this a quarter wave instead of a half wave. I think that's what's happening here. Okay, so in that case, let's just increase that length. So that can be done easily. Go to HFSS, L here. Let's see, 368 times 2. I'm going to do some mental math. 736. Did definitely not use a calculator. 736. Okay. So now let's go ahead and bring back some of our views. So the first thing, we also need to increase our box length. Clearly, it's going to be maybe 1,200 mil, maybe less than that, maybe 1,000 mil. That's an inch. And then the feed line lengths, let's go ahead and make as 500. No, maybe not 500. 400. Maybe a little bit. Maybe we should extend this 1,200. Make this 500. Okay, and let's just add in a couple things to make sure we're still, yeah. So we select the ground plane. We see that we're still we still saved all of our relations. So okay, let's run it again and jump to the space-time portal. Okay, cool. So this was all that was wrong, is I just forgot to do a half wave, and I did a quarter wave, even though it's literally called a half wave resonator. So if we go back to our model, we can do cool things like plot the fields. And for those of you in groups that are designing antennas, a lot of you are designing phased array antennas. So that involves you basically exciting ports, the various ports, in this case we just have 2, with relative phases. Now in this case it doesn't really help us to plot the fields when we're exciting both ports. But for the sake of this tutorial, I'm going to go ahead and show you how to do that. So you would go to, well actually first let's go ahead and add back in the connector in the viewport just for kicks. So add this connector back in here. Okay, cool. So suppose you wanted to put a 0 degree phase on this element and a 30 degree phase on port 2. So you would go to HFSS, fields, and then edit sources. And you can see each one of your, in your field display, you can basically edit how the 2 ports are excited. So I'll excite both of them with the same magnitude, 1 watt coming in, and I'll have 0 degrees at port 1 and 30 degrees at port 2. And I hit apply. And we get something on the output. Of course, this is a silly example to do that sort of relative phasing, since it's just a microstrip structure. But if you're doing an antenna and you want to study like the phased array performance, then it's useful. So I hope you guys found this video helpful, and if you have any questions, you can always email me or Jordan. So thanks a lot.